Okay, here's another simple harmonic motion situation. And this is a nice simple one. This is a mass spring system. And we're asked to determine, we're given some of the properties of the system. And then we're asked to determine the maximum values of speed and acceleration. And then the speed and acceleration when the mass is some distance d from equilibrium. And then finally, the time it takes for the mass to move from equilibrium to some position a minus d. So notice that we're not handed the equation of motion for this thing. We are simply told, it's described to us, right? The physicality of it is described to us. We're asked to determine some of the um, physical behaviors of the system, but it's really up to us to write the position function. So this is useful for us. One of the things that means, or one of the first things you need to decide when you're going to write the position equation for an oscillator is when you're going to start the clock. So when you're thinking about these systems, it's a little different from a system where like you released a ball from the top of an incline or something like that, right? And a natural place to start the clock would be when the object was released. We did a lot of that in 221. So here, this is a system that I want you to think about this oscillator as like it's oscillating when you walk into the room. So say you walk into the lab and here's this oscillator going back and forth. Okay. It's oscillating when you get there, it's oscillating when you leave. If you're going to study this thing, you know that measuring some kind of time is important, right? Because it's in motion, so you care about the time. It's up to you to decide when to start that stopwatch. That is completely up to you. That's a decision that you have to make though before you can write an equation that will describe the motion of this thing. So you have to explicitly decide that in these simple harmonic motion problems, like this one anyway, the kind of more advanced problems where you're being asked to apply the equation to the physical scenario. So there are lots of things I could decide here as my initial condition. I'm going to decide one that um, is a little less popular. I want you to see what it looks like, but it makes sense why I would choose it. So I'm going to say, why don't I just let x equals 0 at t equals 0? Okay. Now, this is not used as much in the lab because normally it's hard to see when if you have an oscillator, it's hard to really see right when that oscillator is going through equilibrium. That's also when it's moving the fastest, it's hardest to time, maybe that kind of thing. Usually students will choose at t equals 0 at x equal a. That's when the object comes to rest for a moment, right? When x equals to the amplitude. And so that's a popular choice. Therefore, the cosine function is kind of the default function that we go to. That's why it's written as a cosine function. But I want to remind you that we can also write it as a sine function. So if I choose my initial condition to be x equals 0 at t equals 0, I can choose a cosine function with a phase shift of pi over 2, or it's the exact same thing is going to be to choose a sine function. I'm going to say that again. I could choose a cosine function with a phase shift of pi over 2, or I could choose a sine function. If phase shifts are still getting to you, stop this video, go back to the oscillatory functions review worksheet and work through that again, and focus on the phase shift part till like you feel like you can really kind of wrap your head around that. All right. Um, so you don't often see these written with a sign, but I wanted to show you that. To a physicist, honestly, the cosine functions and sine functions are exactly the same functions. They're just one is shifted to pi over 2 from the other. But as far as behaviorally, what they can describe as far as motion and such and change is exactly the same thing, right? The functions have the same behavior. All right, so here is my position function. I can then write my velocity function here. That'll be the first derivative of that position function with respect to time. So that's going to be equal to omega a cosine omega t. And my acceleration function, of course, which is just dv dt. Sorry, that's supposed to be a v. Negative omega squared a sine omega t. And notice right now we're seeing one of the hallmark characteristics of simple harmonic motion, right? sometimes students will ask me like, well, how do I know if it's just oscillating, if it's just oscillatory motion, or this special kind called simple harmonic motion? And it's in your book, it's in a lot of different places, but one way you can always tell is that for simple harmonic motion, the acceleration function is equal to some negative constant times the displacement function, or times the position function, I should say. So if you have that case, and notice I've got hats on those guys, these signs represent direction. So we are talking about vectors here. It matters, right? If you're on the one side of the positive side of the equilibrium versus the negative side, it matters. So simple harmonic motion, I have this relationship between acceleration and position, and I have that here. I can see that that showed up in what I chose there. So I know that my acceleration here is equal to negative omega squared times my position function, in fact. So the constant, the proportionality constant, is omega squared in this case. So sometimes students also ask, like, well, why not just then write this as, why do you write it as a negative constant and not negative omega squared? And I usually say that it's different for different systems. For a mass spring system, I would write it in this particular way, but for other systems, you're going to have different, the proportionality constant can be written in terms of the characteristics of the system in different ways, depending on the system. A mass spring system is one that we commonly use for simple harmonic motion, but is certainly not the only system that can have simple harmonic motion. Okay, so what I need to do here now it's a moment for me to do a little bit of force analysis. And this part's really important. Students don't like doing this part of this because it's hard. You have to like really think about what the object is doing, but I say just kind of embrace it and get into it. All right. So we need to do some force analysis. I'll label that here. And we know that we do that with free body diagrams. So the first thing I'm going to draw out is just simply like, here's the spring, here's the block, okay? And let's just first draw it at equilibrium. So it's got some mass M. And let's first draw it at equilibrium, x equals 0. Okay, cool. And let's say going to the right is positive x, and we know that the spring constant we're given there is k. So that's this thing at equilibrium. Great. So at equilibrium, is there any force on the block at all? Nope. That's equilibrium condition. Okay. Um, Now let's think about, we can kind of choose what we're going to do, but I'm going to say, how about we think about compressing this spring? So now we're going to compress the spring, and my block is now right here. So notice the block is now compressed through some, I can call that negative x. All right. Now, when this block is compressed, now there is some horizontal net force on the block, right? Sure. And it's that force that's exerted by the spring. So if I were to draw a free body diagram for the block right here at this point, I'll do it right here. What that free body diagram would look like is, we could say it's on a surface and it has weight and normal force. These aren't going to come into, they're not really going to help me describe my situation here a whole lot, because they are not going to affect the simple harmonic motion piece. However, if I look at what's happening, if I have the mass compressed to the left here, that means that the spring force will be exerted to the right, and that force will be equal to kx. So we get that from Hooke's law. The magnitude of that force is equal to kx. So if I use, if I apply Newton's second law here, what do I get? Is that kx is equal to ma, and I'm applying Newton's second law on the horizontal there. Now, right here is where students will often say, but wait, Hooke's law looks like this. It says that the spring force is equal to negative kx. And then what students will commonly do is just like haul around that negative sign everywhere they ever use a kx, and don't do that. So what the reason the negative sign is in here is because Hooke's law is describing the force that the spring is exerting. And that negative sign, what that's about is saying that if I compress the spring, right, in whatever direction I deform the spring is going to want to go back to equilibrium. And this is true if I compress it or extend it. If I deform the spring in any way, there's always going to be this, the spring is always going to want to go back to equilibrium. And so in order to make that happen, the spring force always has to oppose the deformation, right? I'm going to say that again. The spring force, the force exerted by the spring always has to oppose the deformation. So in a case like this one that we're talking about here, when I compress the spring, I displace the spring to the left, which is in the negative direction. The direction of the spring force would be to the right in order to oppose the displacement and try to restore the system back to equilibrium. It's sometimes called a restoring force for that reason. So that's it's a critical role of that negative sign. But the negative sign only belongs in there when you have Hooke's law written out in its vector form and you're considering those directions. Notice for this free body diagram, I've got the direction. I already used the a theory of Hooke's law to figure out that yes, the spring is going to be pushing to the right because it's trying to restore back to equilibrium, even though the displacement is to the left. So I have a leftward displacement and a rightward directed spring force. That is what the sign in Hooke's law is handing me. Okay. However, once I notice that, like with any free body diagram, I label these forces. I have their directions on my analytical diagram, and then I label the forces with their magnitudes. So Kx is in the positive direction. That is going to be positive in my Newton's second law statement. Acceleration then will also be to the right, which is positive. If I were to throw an arbitrary negative sign in front of that Kx, that would be incorrect. Okay, that's I think is worth spending time on because I see that mistake so often. This is the equation then that I have here, Kx is equal to ma. The reason I'm doing this is that I can take this equation and solve for acceleration here, Kx over m, and put this together with my acceleration, write this as a magnitude, a is equal to omega squared x. So notice I dropped the negative sign, but I also dropped the hats. The negative sign is about the vectorness of this, right? Is about the direction. I can also go and be relating magnitudes to one another, and that's okay for me to do that. I'm just saying the magnitude of the acceleration is equal to omega squared times the magnitude of the displacement, right? Okay, I'm going to put those two equations together. Kx over m is equal to omega squared x, and that gives me an all-important equation that omega is equal to root k over m. All right, so this is really, really important. What that was is just a derivation of the angular frequency, sometimes also just referred to as the frequency, but I'll always call it the angular frequency when I'm talking about omega versus just f, right? The angular frequency of the system is basically based on the properties of two things. What is the spring constant of the spring and what is the mass of the block? And if I know the spring constant and the mass of the block, then I can fully describe how my system is going to operate. Okay, um, so I'm interested in the maximum values of speed and acceleration for the system, right? If I look at my velocity equation, I'm going to go back up here to my velocity equation. If I look at that, I can see that how does that max? Well, cosine omega t has a maximum value of 1, right? So knowing that, cosine and sine both have that maximum value of 1. V max, the maximum value of speed, here I'm just thinking about magnitude here, is then going to be equal to omega a. So now I know that I can write that as a root k over m. The maximum value of acceleration, Same thing, I'll look at my acceleration function here, and I can see that I know the maximum value of sine is going to be 1, and I'm just looking at magnitude here. So the maximum acceleration will be equal to omega squared times a, which in this case will be k a over m. So this here is my answer for part A. All right, moving on. The speed and acceleration when the mass is some distance d from the equilibrium position. Well, I already have my velocity and acceleration functions, right? I have those two functions, and I just need to find what those would be at x equal d, so I can substitute into those. And note that now I have, in place of the omega, I know that that's equal to root k over m, so I can substitute that in for omega. And then I'm interested in the values of those things when x is equal to d. So you might say that, like, well, if I look at this though, how can I have this speed, but it's, or velocity in this case here, I have the hat on it, but it is only with respect to time, right? I don't have it with respect to position. So it's true that you do need to find the time at which x is equal to d. So you can do that by looking at your position function. So my position function I wrote as x equals a sine omega t. So if I'm interested in time, remember, sine omega t is equal to x over a. T is equal to 1 over omega arc sine x over a. And what does that look like for us? That 1 over omega is root m over k arc sine x over a. So that's my general function for time. Now I'm interested in the time at which x equal d, right? So when x is equal to d, t, and you can call this, I don't know, t sub d if you want, is equal to root m over k arc sine d over a. And that's my time. Now that's important because this is the time that I can then sub into my velocity equation, right, to get the speed at x equal d. So I can say here, at x equal d, the speed is equal to root k over m a cosine. Now this is my time, right, in here, part of my time, arc sine of d over a. Okay. So that is how I'd find the time there. And you could go through the exact same process to find the acceleration. So it's like it was in your kinematics before, right? Where you can find the time. If you're asked to find the velocity, in this case, we're asked to find the speed at a particular position, or velocity, I think, at a particular position. We need to find the time at that position first. And we can do that because we have the position versus time function, right? So you take that function, kind of turn it inside out to define the time at a certain position, and then you can use that time in your other functions. Okay, so that would be how you would approach B. Now, part C here asks us for the time it takes the mass to move from equilibrium x equals 0 to x equal a minus d. And I'll be honest, this is one of the reasons that I chose my initial condition to look like this, x equals 0 at t equals 0, because then all I have to do is find the time when the position is equal to a minus d. And I know that's the answer to part C. I don't have to subtract anything else because I started my clock at x equals 0. So we already know how to do this, right? How to find the time at a particular position because we just did that. for this part here. So you would go through the same process, but instead of substituting in D, you'd substitute in the position A minus D for that part. As usual, all the details are in the written solution.